Great. So Home couldn't come to be physically here, but he's in Haifa and will tell us about KRW and communication complexity. Thanks.
Thank you, Avi. This is how the talk is going to work. I'll start with the relevant background, and then I'll discuss our result and the motivation for it. Then I'll sketch our proof strategy, and eventually I'll say a few words about two nice technical ideas from our proof that might be of interest. At least I hope so. Okay, so let's start with the background. So first of all, in this talk, our model of computation is going to be Boolean circuits. Unlike RAM machines or Turing machines, we are going to work with the logical circuits that we all know and love from our introduction to hardware courses, classes in the undergraduate degree that have AND gates, OR gates, and negation gates. Important complexity measure about these circuits will be the size of the circuits, which is the number of gates. And even more important for this talk is the depth of the circuits, which is the length of the longest path from an input gate to an output gate. Intuitively, you can think about it as how many layers the circuit has, or maybe how much time it takes to simulate the circuit on a parallel machine that can simulate a single layer in a single step. Now, there are many models of circuits. In this talk, we will focus on circuits that have fan-in 2. That is, we are going to assume that every gate has at most 2 incoming wires. Now, the general topic of this talk is circuit lower bounds. And so what is this about? Well, in complexity theory, as you probably know, our goal is to prove hardness. For example, we want to prove that a function is hard to compute in the sense that it doesn't have circuits of size polynomial in N. Now, it should be said that in general, this is easy to prove such a statement. I mean, we know by an easy counting argument that there exist some functions that for which, if we want to compute them, we have to use circuits of size that is roughly exponential in N. But this is not that interesting. What we really want to prove it is not for some function. We want to prove it for a function that we really care about, a function that we can describe, an explicit function, ideally a function in NP. And this is what we are trying to do in circuit lower bounds. Unfortunately, proving such results for general circuits is extremely hard. In particular, it would imply that is different than NP, so we can't do it yet. So what we do in the meantime is trying to prove hardness for weaker models of circuits. Where the hope is that if we can one day prove such results for very weak models of circuits, and maybe then we will be able to prove lower bounds for slightly stronger circuits, and then slightly stronger circuits, and so on, until we can prove strong results for general circuits. And in this particular talk, we will focus on one such weak model, which is called small depth circuits. Let's be more specific now. So given a Boolean function f from 0,1 to the n to 0,1, we define the depth complexity of the function to be the depth of the shallowest circuit that computes the function, regardless of the size of the circuit. Now, since we assumed that all the circuits we consider have fan-in 2, then it is easy to see that every interesting function has depth complexity at least log n, because a circuit of depth less than log n cannot read all its inputs. On the other hand, it is a major open question in complexity theory to come up with an explicit function, ideally a function in P, that has super-logarithmic depth complexity. This is known as the P versus NC1 question. And it is one of the major frontier questions in these days in circuit complexity. Now, what is the state of the art about this question? Well, we know since 93 that we can that there is a function in P that has depth complexity roughly 3 log n. And in 14, Tal improved the lower order terms in this result. Okay, so this is the general question we are going to study. Any questions so far?
Oh,
Okay, so the results are great, but it seems that they have reached their limit. I mean, it doesn't seem like we can use their techniques to obtain anything better. So the question is, what do we do now? And in this talk, we focus on an approach that was suggested by Karchmer and Wigderson in 91. And there he suggested that we should try to understand the composition of Boolean functions. What do I mean by that? Well, let's say that we have two Boolean functions, f over m bits and g over n bits. Now, obviously, we cannot compose them in the standard way because the output of g is smaller than the input of f. But we can define the composition in the following natural way. So the composed function will take as inputs m by n Boolean matrices. And in order to compute the function on such a matrix, we first observe that the rows of the matrix are strings of length n, so they are legal inputs of the function g, and therefore we can compute the function g on these rows. Now, once we do that, we get a column vector, which we will denote by a, and this column vector is a string of length m, so it is a valid input of f. So we can compute f on this column vector, and now we define the resulting bit to be the output of the composition. Now, this is the most important definition in this talk. So if you have any questions about it, please ask me. Okay. Yes, question? Okay. So now that we have this definition of composition, it makes sense to ask how does depth complexity behave with respect to this notion of composition. And the first easy observation is that the depth complexity of the composed function is at most the sum of the individual depth complexities. Why is that? Well, if we compute the composition in the just according to the definition I described, we get exactly this depth complexity. Now, Karchmer and Wigderson conjecture that this is actually the best way, more or less, to compute the composed function for every two non-constant functions. And this is a very natural and interesting conjecture on its own right, but they also observe that if we could prove this conjecture, this would imply that a separation of P from NC1. That is, they prove that if this conjecture implies that a solution to this major open question of complexity theory that I mentioned earlier. This makes, of course, the conjecture even more interesting. And indeed, by now, there have been multiple works on this conjecture that proved several interesting special cases. Nevertheless, we are still far from proving the full conjecture. By the way, the use of approximating inequality here is intentional. The reason is that there are multiple interpretations of this approximating equality, and all of those interpretations would yield separation. So I don't want to commit to one of these interpretations yet. Now, okay, so this is the KRW conjecture, but it turns out that we can weaken it a bit. So the KRW conjecture says that for every non-constant function f and for every non-constant function g, this approximate equality should hold. But if we only care about proving that P is different as an NC1, then it is actually sufficient to prove something weaker. It is sufficient to prove that for every non-constant function f, there exists some hard function g for which this approximate equality holds. To be more concrete, let's put forth the following conjecture, which we'll call the weak KRW conjecture, which says that for every non-constant function f and every input length n, there exists some hard function, some function g over n bits, such that the depth complexity of the composed function is larger than the depth complexity of f by something that is super-logarithmic. Now, note that in this conjecture, we do not require the function g to be explicit. That is, we do not require it to be in P. In principle, we could have proved it using a counting argument. So this makes this conjecture at least seem to be much easier. And indeed, a few years ago, there was a result in this direction by Mihajlin and Small, who proved such a result for the for a variant in which we replace the outer function f with something called the universal relation. Now, I don't have time to go into what this universal relation is, so let me just say that if we want to get a circuit lower bound out of it, then we really have to replace the universal relation with some proper honest-to-God function. So this is what we really want to do, and in this work, we take another step toward this goal. Any questions up until here? Okay. Okay, so next. So this is the KRW conjecture. Now let's see how we can attack it. So the main tool that is used in studying the KRW conjecture is something called KW relations, Karchmer-Wigderson relations, which is an old observation due to, of course, Karchmer and Wigderson, which says that we can analyze the depth complexity of a function by studying the communication complexity of a related communication problem. Now, this communication problem is called the KW relation of f, and it is defined as follows. We have two parties, Alice and Bob. Alice gets a string x on which f outputs 1. Bob gets a string y on which f outputs 0. Now, clearly, these are two different strings, so they must disagree on some coordinate. And the goal of Alice and Bob is to find some coordinate that satisfies this, and they want to do so by while communicating as little as possible. Now, what Karchmer and Wigderson observed is that the depth complexity of f is equal exactly to the communication complexity of the KW relation of f. That is, it is exactly equal to the minimum number of bits that Alice and Bob have to communicate in order to find such a coordinate. Now, using this terminology, we can rephrase the KRW conjecture as follows. The communication complexity of the KW relation of the composed function is roughly the sum of the communication complexities of the individual KW relations. Now, so it makes sense to try to use this perspective to study the KRW conjecture. And in order to do so, we just need to understand how the KW relation of the composed function looks like. So let's do that. Let's recall that the composed function takes inputs which are m by n matrices. So this means that in the KW relation, the players will get inputs that are m by n matrices, which we will denote by x and y. And their goal would be to find an entry on which these two entries differ. Now, to this end, they are given the following promise. So they are promised that if they compute G on the rows of their matrices, they'll get two column vectors, which we will denote by A and B, such that if they compute F on these column vectors, they will get 1 and 0 respectively. And they want to use this promise in order to find this entry. Now, it is useful so we want to prove the communication complexity of this problem is roughly this sum of communication complexities. And it is useful to see why this is an upper bound from the perspective of communication complexity. So to see it, let's observe that there is an obvious protocol that solves this problem. The obvious protocol starts by observing that the column vectors A and B on their own are a valid input of the KW relation of F. So we can find so we can use the optimal protocol for the KW relation of F to find some coordinate on which A and B differ. Now, and once we found it, we can look at the corresponding rows of X and Y and observe that the function G outputs different values on these rows because, well, this is how the vectors A and B are defined. But if G outputs different values on these rows, then they on their own are a valid input of the KW relation of G, and therefore we can apply the optimal protocol for the KW relation of G in order to find the coordinate on which these rows differ. And this coordinate is going to be the entry ij that we are looking for. So the communication complexity of this protocol is the sum of the two communication complexities of F and G. And the KRW conjecture amounts to saying that this protocol is essentially optimal. Okay, so this concludes the background part. Any questions? Everyone lost me so quickly. Okay.
No question.
Yes, Ian.
I didn't lose you, is all I'm saying.
Okay. Okay, great. So let's move on to discuss our result, and let's start with a motivating discussion. So I said that the KRW conjecture basically says that the obvious protocol is optimal. So let's ask, why should we believe that? Why should the obvious protocol be optimal? So there is actually a nice intuition for that. Well, first, I'd like to argue that the pairs have to look for the solution entry in a row where AI is different than BI. Why is that? Well, basically, these are the only rows on which the pairs have any sort of a handle. And in particular, in all the other rows, we are not even guaranteed that there is a solution. That is, we are not even guaranteed that there is an entry on which the matrices differ in the other rows. However, if the players wish to find the solution entry in a row where AI is different than BI, then they must first find such a row. Now, the point is that finding a row where AI is different than BI is equivalent to solving the KW relation of F on A and B. Moreover, once they found such a row, looking for an entry on which the matrices differ inside the row is equivalent to solving the KW relation of G. So it seems like the players are just forced to solve both the KW relation of F and the KW relation of G, and therefore they have to communicate a number of bits which is equal to the sum of the communication complexities of these relations. Now, this intuition sounds very appealing, and indeed in some previous works we managed to turn this intuition into a proof. But in general, it is very difficult to turn this intuition into a formal proof, mainly due to two obstacles. First, we argued that the players have to find the solution entry in a row where AI is different than BI. And this sounds very convincing, but of course, we cannot just assume it. We have to prove it. And in general, it is very difficult to prove it. Second, even if we could prove that assumption, and even if we could actually prove that the players have to solve both the KW relation of F and the KW relation of G, this would still not be sufficient to imply that the players have to communicate a number of bits, which is the sum of the communication complexities. Why not? Well, maybe the players have some very clever strategy that allows them to solve both KW relations simultaneously, using the same bits and therefore saving the communication. I mean, there is no reason to believe that the players have to solve those two problems separately. Maybe they can use the fact that they are solving both of them together to save communication. And these kind of questions are called, in general, in complexity theory, direct sum problems. And in general, we do not know how to prove direct sum theorems in communication complexity, at least not for KW relations. So this is another obstacle.
Maybe you should that in some models direct sum does not hold. Sometimes
Yes, you're right. There are models of computation in which direct sum theorems do not hold. In communication complexities, they might hold, but we can't prove it. Okay, so our goal in this work is to focus on the second obstacle, on the direct sum problem. And while doing so, we want to avoid dealing with the first obstacle and leave it for some other day. So in order to do this, we focus on a notion called the Stone composition of two KW relations. And this notion of Stone composition is defined exactly like the KW relation of the composed function, but with the added limitation that the solution entry ij must be in a row where ai is different than bi. That is, we define this notion of Stone composition exactly such that it avoids the first obstacle I mentioned in the previous slide and just gives it to us for free. And now that we have this notion, it makes sense to ask, well, can we prove the KRW conjecture for the Stone composition of F and G? And this is a very natural and interesting question on its own right. And in particular, one nice thing about it is that it is necessary for proving the KRW conjecture for Stone composition is a necessary step toward proving the original KRW conjecture, because the original KRW conjecture implies it. Moreover, another nice thing about this conjecture is that it allows us to focus on solving the direct sum, on dealing with the direct sum aspect of the KRW conjecture. So now that I've explained all this lengthy background, I can finally state our result. So our result is a sort of a weak KRW theorem for Stone composition. That is, recall that the weak KRW conjecture said that for every f, there exists some Rg for which the KRW conjecture holds. And we prove such a result for Stone composition. To be more specific, we prove the following result. For every non-constant function f over m bits, and for every input length n, there exists some function g over n bits, such that the communication complexity of the Stone composition is greater than the communication complexity of the KW relation of f, plus n, which is the input length of g, minus 0.96m, which is the input length of f, minus some lower order term. Now, note that actually, if we had, instead of the 0.961, that is, if we lost minus m in this result, then this theorem would have been trivial. It is just vacuously true that it has to be at least this minus m. The move from minus m to minus 0.96m is what we actually gain in this result. And this might not sound that impressive. So you might be asking yourself, how does this relate to the weak KRW conjecture I mentioned earlier? So let me say this. If we could prove such a result for standard composition rather than for Stone composition, that would give us a depth complexity lower bound of at least 3.04 log n. That is, we would get the first improvement in lower bounds since the work of Hasted in 93, the first improvement in depth complexity lower bounds in 3 decades. It would be a modest improvement, but I think it would be an exciting improvement nevertheless. However, unfortunately, this kind of result would not be sufficient for separating P from NC1, exactly due to this annoying loss of 0.96m. And I hope someone here might be able to get rid of this loss. Questions so far? Okay, so this is our result. Now let's talk about how it is proved. So let's fix some arbitrary function f over m bits and some input length n, and our goal is to prove that there exists some function g over n bits such that the stone composition, the communication complexity of the stone composition is large. And to this end, we define an auxiliary communication problem, which we call multiplexer composition. And this is defined exactly like the original stone composition, but now the function g is not some arbitrary function that is fixed in advance. Rather, it is an input of another input of the players. That is, now Alice and Bob take as inputs the function g, and both get the same function g, and they get matrices x and y. And their goal is to now solve the stone composition of KWF and KWG on the matrices x and y for the function g that they got. Now, why am I defining this auxiliary communication problem? Well, it turns out that if we can prove a lower bound for this problem, then we will get the result we want. That is, it suffices to prove that the communication complexity of this problem is at least the communication complexity of f plus n minus the loss term that we got that was stated in the in the statement in our result. Now, I should say this implication is not trivial. We are using here a technique from the paper of Mihajinen and Small, and moreover, not really sufficient to prove a standard lower bound for this communication problem. The lower bound actually has to be proved in another more sophisticated communication model, but I'm not going to get into that. Okay, so now from now on, our goal will be to prove a lower bound for this problem. So how do we do that? Let's recall that our goal is to prove that the obvious protocol is optimal, and the obvious protocol goes by first solving the KW relation of f on A and B, and then solving the KW relation of G on xi and yi. Now, our challenge is to prove that Alice and Bob cannot solve both KW relations simultaneously faster than they can solve each of them separately. They cannot somehow make use of the fact that they are solving both of them together. And why should this be true? Well, the intuition is that Alice and Bob must first finish solving the KW relation of f before they even start solving the KW relation of G. Why is that? Well, intuitively, until Alice and Bob finish solving the KW relation of f on A and B, they don't know on which row they should be solving the KW relation of G. So how can they make progress on solving KW relation of G if they don't even know on which input they should be solving it? And of course, if they have to first solve f before they solve G, then they cannot make use of the fact that they are solving both relations together. And this intuition, and we are going to turn this intuition into a proof. By the way, this proof strategy is not our invention. It goes back to Edmonds et al. In 91, and it has also been used in several other works on the KRW conjecture since then. So what we are going to do now is to pick some protocol that solves the multiplexer composition, and let's say we want to prove that it has to communicate many bits. Then we are going to prove two things. First, we are going to prove the following intuitive statement. As long as pi does not finish solving the KW relation of f, it cannot make progress on the KW relation of G. Now, this statement is of course very rough and very intuitive and very informal. So let me make it a bit more formal. We are going to prove the following structure theorem for protocols that solve the multiplexer composition problem. let's say that we look at any partial transcript of the protocol. That is, let's say that we are looking at any intermediate state of the protocol. The partial transcript is just an intermediate state of the protocol. And let's look at such a transcript in which the players are still far from solving the KW relation of F. And moreover, the players have still not transmitted a lot of information about their inputs. Think about it. Let's say here we are imagining that there is some third party that looks at the protocol and listens to what Alice and Bob says. And we assume that this third party has not learned a lot about the inputs of Alice and Bob from listening to their conversation so far. Then, if this transcript, this intermediate state satisfies these two assumptions, then we can show that after reaching that when the protocol is at this state, the players must still communicate roughly n more bits. By the way, why do we have n here? Because, because n is the communication complexity that is required to solve the KW relation of G for every possible function G.
Oh, just a clarification. Partial transcript is just all the bits that were transmitted until the point.
Yes. A partial transcript, one way to define it is, as I said, an intermediate state of the protocol, but another way to look at it is just a string that contains the bits that Alice and Bob sent in the protocol so far. Sorry, I couldn't hear you.
Yeah.
Was there another question?
No.
Oh, okay. I thought I heard someone. Okay, so let's say that you believe me that this structure theorem is true. Well, this now more or less almost finishes the proof. Well, it is not very hard. It requires a proof, but not a very complicated one, to prove that there exists some partial that for every protocol that solves the multiplexer composition, there exists some partial transcript pi1 that satisfies these properties and is of length that is roughly the complexity of F. And once we prove the existence of such a partial transcript, we apply this theorem to the partial transcript, and we get that, and now we get that the protocol must transmit at least this many bits in the worst case. Why? Because we know that in order to transmit this partial transcript, Alice and Bob transmitted this many bits, and after they transmitted this partial transcript, they still have to transmit roughly n more bits. So all in all, we get it in the worst case, they have to transmit this many bits. Questions so far? Okay, so this is the overall proof strategy. By the way, so far it is not very original in the sense that it was really such tricks were employed heavily in previous works. Now we are going to get into the more interesting part, at least for me. But hopefully for you too. Okay, so I won't have time to describe the proof in detail, but I do want to go over two technical ideas that I think are very nice and might also be of independent interest. So the first of them is using graph coloring to deduce lower bounds. And so let's recall where we are. Our goal is now to prove the structure theorem that I stated in the previous slide. So we fixed some partial transcript pi1 that satisfies the properties that I stated. And our goal is to prove that the players must communicate roughly n more bits. And to this end, I'm going to use another technique of Mihajlin and Small. And in order to explain this technique, I need to set up some notation. So this is what I'm going to do now. First, I'm going to define two sets. For every function g over n bits, I'll define the set calligraphic x of g, which is just a set of all matrices x, such that the pair g comma x is a legal input of Alice, and moreover, it is a legal input of Alice that is consistent with the partial transcript pi1. That is, if we see that the protocol transmitted the partial transcript pi1, then from our point of view, it is possible that Alice has the input g comma x. The partial transcript pi1 does not rule out this input. Second, I'm going to define the set calligraphic y, which is just defined in the same way for matrices y and Bob. Now, using this notation, I'll define a notion called intersecting functions. So I'm going to say that two functions from n bits to 1 bit intersect if either the set calligraphic x of g1 intersects the set calligraphic y of g2, or the other way around, the set calligraphic x of g2 intersects the set calligraphic y of g1. Okay, so now we are getting into technical details, so I guess it takes a bit more time to process it. Can I help, and are there any questions?
So in particular, the fact that x intersects y of the other function means that they could have flipped the function value, right, between them.
I'm not sure I'm following. I mean, yes. Oh, so yes, it means that there is some matrix in the intersection that in particular, the composed function f and f composed with g1 outputs, say, 1 on this matrix, and f composed with g2 outputs 0 on this matrix.
Yeah.
And again, the other way around in the case of the second condition. Okay, so yeah.
For pi1, in the beginning of the protocol, all of them intersect.
Yes. No, sorry. Let me think about it more for a moment. No, not exactly. Okay, first of all, a matrix cannot intersect itself. Sorry, a function can never intersect itself. And whether two different functions must intersect, well, I remember I thought about it some time ago and I realized that, well, you could think about some extreme cases in which they do not intersect. For example, if G1, G2 is the complement of G1, then you might be able to construct the function. Then they might not intersect. But other than extreme, sorry?
Yeah, most of the pairs intersect, and what happens with communication is you keep losing such intersection.
Exactly. So first of all, except for some extreme edge cases like this, all functions intersect. And moreover, yes, that's exactly the point. The more information that is passed through the partial transcript, the more the players communicate, intersections get lost. Now, if you are fine with this definition, then I can now state an important lemma that is implicit in the work of Mihajlin and Small. And this lemma says that, okay, intuitively it says the following. Suppose that I could find many sets, many functions that are pairwise intersecting. That is a very large set of functions such that every two functions in the set intersect. Then if I can find such a set, then after the players reach the partial transcript pi1, they still have to communicate many more bits. How many more? Well, log the size of the set.
Log is consistent with the fact that there are 2 to the n functions on n bits.
Yes, exactly. I'm going to get to it. So, but before I get into more details about this lemma, let me mention that this lemma, well, it wasn't really stated in the word of Meir and Small, but what the technique does works for standard composition. It's not stated, it was not developed for strong composition. It was developed for standard composition. So in principle, this technique is useful also for the original KRW conjecture. And moreover, yes, that's the point. That in order to use this lemma, we would like to construct such a set V of which is of size 2 to the 2 to the n, which is indeed fine because this is more or less the number of all functions. So as long as we get almost all functions in the set, or maybe all functions, or maybe let's say a not too small function of all functions, then we will be fine. Unfortunately, it is not that easy to construct such a set. In particular, one thing that is kind of annoying in trying to construct such a set is that it's kind of difficult to construct a set in which every 2 functions intersect. It is relatively, okay, we don't want to say easy, but easier to construct a set in which, say, most pairs of functions intersect. But getting a set in which every 2 functions intersect is kind of annoying. And so it would have been nicer if we had a more flexible condition here. And in order to get such a condition, we move into a theoretic perspective. So, and in particular, I'm going to define something that I view as a very natural notion called the characteristic graph of the partial transcript. And this is a graph in which the vertices are all the possible functions over n bits. And 2 functions are neighbors or adjuncted in this graph, if and only if they intersect. And once we define this graph, this lemma of Meir and Small can be restated as follows. After reaching the partial transcript by 1, the players must still communicate a number of bits which is log, the click number of the characteristic graph. Here, omega of the graph is a parameter called the click number, which is just the size of a maximum click in the graph. Why is that? Well, if we go back to the previous slides and we see that in the terminology of the characteristic graph, such a set V that has this, in which every 2 functions intersect, is just a click in the graph. So this lemma says that for every click, we get a lower bound that is double logarithmic in the size of the click. And in particular, we get a lower bound that is double logarithmic in the size of the maximum click. And now, in this work, we generalize this lemma to get a similar lower bound, but now we get something that is double logarithmic in the chromatic number of the graph. That is the minimum number of colors that is required to color the graph, such that every 2 vertices are colored with a different color. And it turns out that this condition is simpler. It turns out that, at least for our purposes, it is simpler to work with the chromatic number. In particular, one nice thing about it is that this lemma means that now, instead of trying to construct a very large click, we can try to upper bound the size of the largest independent set, which turns out to be somewhat simpler. Now, in retrospect, after I wrote the first draft of the paper, I found out that actually I could prove this result using the original lemma of Meir and Small, but that would have been more complicated and it would actually still require the perspective of graph theory. I would actually need to apply some graph theoretic tricks in order to do that. But once we have this lemma, everything is much simpler. Another nice thing about this lemma is that this lemma too works for standard composition. That is, our generalization too can in principle be used to study the original KRW conjecture, or at least the original weak KRW conjecture. Questions? Okay, so as I said, all of this machinery works for standard composition, but our goal in this work is to prove a lower bound for strong composition, and this is supposed to be a simpler task. So let's see how can we make use of that. So if you recall, in strong composition, the players have to look for a solution entry ij in the row where ai is different than bi. And it turns out that this same machinery that I stated in the previous slide works just as well, except that we need to change it a bit such that it only cares about rows in which ai is different than bi. In particular, we need to change our definition of intersecting functions such that it only cares about rows where ai is different than bi. Specifically, we have the following definition. We say that two functions g1, g2 weakly intersect if they satisfy the following property. There exist two matrices, one matrix x in the set calligraphic x of g1, and another matrix y in the set calligraphic y of g2, such that x agrees with phi on all the rows where ai is different from bi. Now, to see the connection between the definitions, let's just observe that I could have restated the previous definition of intersection as saying that there are two matrices, x in calligraphic x of G1 and y in calligraphic y of G2, that agree on all the rows. I mean, what I said earlier is that these two sets, calligraphic x of G1 and calligraphic y of G2, are these two sets intersect, and this is equivalent to say that there is some matrix that exists in both these sets, which is equivalent to saying that there are two matrices, one on each set, that agree on all the rows. So now I'm just weaken this condition to say that the matrices only need to agree on the rows where ai is different than bi. And of course, I also allow the other direction, where x is in calligraphic x of G2 and y is in calligraphic y of G1. Now, I hope that I convinced you that this is really a relaxation of the previous definition. So even though this definition is quite more complicated, it is actually easier to satisfy this definition. Questions?
The intuitive reason why it will be easier is that the pi1, the given pi1, is not long enough to touch all the rows in the matrices.
Okay, it's a maybe you could, yeah, I guess you could look at it like that very roughly, that to say that, well, because the partial translate pi1 did not give much information on the matrices of the players, they cannot touch all the rows, and since they also didn't solve the KW relation of F, they also don't know where AI is different from BI, so we can somehow make sure that if they found any differences between the rows of X and Y, those differences are concentrated in rows where AI is not different from BI, where AI is actually equal to BI. That's a very rough intuition for the proof. But maybe a more straightforward reason why this is easier to satisfy this definition is because in the previous definition of intersection, we had this very strict condition that we have to agree on exactly all the rows. The same matrix has to appear exactly in both the set of G1 and in the set of G2. And this definition is more flexible. It says, okay, if you have a few rows that you don't, some rows that you don't like, some rows that you don't want to agree on, then, feel free to throw them away as long as you can guarantee that AI is equal to BI on these rows. Does this, I mean, does this help? Okay. Okay, so this is all I had to say about this particular part. And now in the last part of the talk, I want to introduce another nice technical idea from this work, which I call prefix fixed sets. And even if you lost me so far, you may want to listen to this part, at least after the first slide, because this technical idea, I believe, might be of use also outside of the context of the KRW conjecture, and maybe outside of the context of complexity theory in general. Let's start from the beginning. So our goal was to prove a lower bound of the chromatic number of that characteristic graph. And to this end, we need to prove that functions weakly intersect. So let's ask this abstract question. How can we prove that two functions weakly intersect? So let's recall the definition. Our goal is to prove that there is some matrix X in the set calligraphic X of G1 and a matrix Y in the set calligraphic Y of G2 that are equal on the rows where AI is different from BI. Or vice versa, but let's not say it every time. Okay, so how can we do that? Well, now is the time to use the assumptions we made on the partial transcript pi1. That is, if you recall, when we stated our structure theorem, we made all these assumptions on the partial transcript pi1, and now we are going to use them. So due to those assumptions, we can assume two things. First, I'm going to assume that the set calligraphic X of G1 and calligraphic Y of G2 are large. Specifically, I'm going to assume that they have density like 2 to the minus epsilon m, where epsilon is some small constant. And why can I make this assumption? Well, this basically follows from the assumption that pi1 does not reveal too much information about the inputs of the players. Second, I'm going to assume that this condition AI is different than BI does not hold for too many rows. It holds for at most alpha times m rows, where again, alpha is some small constant that I'm not going to specify. Why can I make this assumption? Well, that's a bit tricky, but basically it follows from the assumption that pi1 is that when we get to the partial transcript pi1, the players are still far from solving the KW relation of F. So you are not supposed to see why this implication holds, just believe me that it can be done. And it's not that hard. Okay, so now let's see what we get if we combine these assumptions with the thing we want to prove. If we think about it, we see that from these assumptions, we can try to first try to prove something simpler. That is, let's think about the following warm-up goal. If we want to prove that there exists such matrix X and matrix Y that agree on the rows where AI is different than BI, and we know that there are at most alpha m rows in which AI is different from BI, then we can, for start, try to prove that there exist two matrices X and Y that are equal to at least alpha m rows. And this is now this is not really a question in complexity theory. This is more of a question in combinatorics. So let's phrase it like a proper, nice question in combinatorics. Let's instead of thinking about matrices, let's think in more abstract terms. Let's think about strings over some finite alphabet. So we will think about our matrices in particular as strings where every strings of length m, where every symbol is a full row of bits. So now we have two sets, calligraphic X and calligraphic Y, that are two sets of strings over some finite alphabet of length m, and they are relatively large. They are strings of density at least 2 to the minus epsilon m, where epsilon is some small constant. Now, here is a nice question in combinatorics. Prove that given these conditions, there exist two strings, X in calligraphic X and y in calligraphic y that agree on at least alpha times m coordinates for some small constant alpha that depends only on epsilon. Now, this is a nice question in combinatorics, and it turns out that there are a few ways to solve it using known techniques in combinatorics, but I'm going to choose a particular solution that is not only nice, but also useful for the original setting. But before I introduce it, let me rephrase this question in another way. Our goal is to prove that there exists some set of coordinates I of size at least alpha m, such that the projections of calligraphic x and calligraphic y to these coordinates intersect, that these two sets intersect. So this is just a different way to put this toy problem. And what I'm going to do is to show that I can choose this set I to have some nice property that I'm going to call prefix Zik sets. In particular, it's going to have the property that the set the projections of calligraphic x and calligraphic y to the coordinates in I are prefix Zik sets. So now I'm going to define this property. And this is where I think the contribution of this paper might be useful in other contexts as well. So given any set of strings over some finite alphabet, I'm going to define a property called prefix Zik, which says that every string W, which is a prefix of strings in calligraphic X, has many ways to extend it by one symbol while still getting a prefix of string in X. In particular, for every such prefix W, I can extend it to a prefix that is longer by one symbol in a number of ways, which is more than the size of the alphabet over 2. And I think that this is a very natural definition. In particular, it has a very nice information theoretic intuition. This definition basically says that if someone gives you a prefix of, if let's say someone has in mind a string in a set, and they give you a prefix of this set, of this string, then this prefix gives you at most less than one bit of information on the string, on the next symbol in the string. Now here is an easy observation. This is maybe not immediate, but it's an easy exercise to show that if you have any prefix Zik subset of sigma to the m, then they must intersect. Every two prefix Zik sets must intersect. Basically, that's because, well, they must have some common prefix of length 1, just because the property of prefix thickness says that each of the sets has more than sigma over 2 prefixes of size 1 of length 1, so they have to intersect somewhere. And then we can again find a common prefix of length 2 using this property, and so on and so on. So now, given this observation, we can see why it solves our combinatorial tree problem, because if we can find a set of coordinates I of size at least alpha m, such that both projections of calligraphic x and calligraphic y to I are prefix Zik, then we immediately get that they intersect, and this solves our problem. Okay, so now the question is, can we find such a set of coordinates on which such that both projections are prefix Zik? And to this end, we prove the following lemma, which might be of independent use. Let's say we have any set of strings of any density delta. Then many projections of this set are prefix Zik. In particular, or at least beta fraction of the sets of coordinates, the projection of x to to these coordinates is prefix C, which is a general lemma that might be useful. And actually, the proof of this lemma follows rather easily. This lemma follows rather easily from a result about discrete dynamical systems. It turns out that in the literature of discrete dynamical systems, they studied similar questions, and this lemma follows directly from a more general result in this literature.
Oh,
yes.
It's not just a simple entropy argument. If you give only epsilon m bits about the set, then there are many coordinates which have entropy close to 1, and this will be
yes, but this kind of argument would tell you that this is true for most prefixes, and we want it for all prefixes. I mean, an entropy argument would work for the average prefix. We want something that works for every prefix.
But you get a conditional. Well, okay, doesn't matter. Later.
Okay. Okay. Now, another nice thing about this lemma is that it can be viewed as a. But okay, let me say that this result in discrete dynamical systems is also not that hard. I mean. In the original paper, there is a proof of half a page. In my paper, I wrote a self-contained proof in what I think is a nicer way, so it takes 2.5 pages. It's not that hard. Okay, I also want to point out that this lemma could be thought of as a nice generalization of the Sauer-Shelach lemma to large alphabets. If you're familiar with the Sauer-Shelach lemma, then you can know that if we think about the alphabet sigma as the binary alphabet, then the notion of a prefix 6 set, well, the only prefix 6 set there is in this case is the full set of all possible strings of length m. And the projection of the set to some coordinates in I is prefix 6, basically, if this projection is shattered by I. So the notion of shattered sets and prefix 6 projections is the same in this case. So, and this lemma is just a generalization of the Sauer-Shelach lemma to larger alphabets. And it is not just a qualitative generalization, it's actually a quantitative generalization. We get exactly the same parameters as in the Sauer-Shelach lemma. Okay, so this is basically more all I had to say about this part. So let's just wrap up and put everything together. So using the last lemma, we can find a set of coordinates I such that both the sets calligraphic x of g1 and calligraphic y of g2 when projected to I are prefix 6. And this says that there is now this requires some more work and some and a few more non-trivial ideas to actually prove that many pairs of functions weakly intersect, but this is our starting point. And but once we can prove that many pairs of functions weakly intersect, we can prove the existence of many edges in the characteristic graph. And this allows us to prove lower bounds on the chromatic number of this graph, which finally gives us the communication complexity lower bound that we want. So let's really conclude. So the KRW conjecture is a promising approach for separating P from NC1, and even a weak version of this conjecture would suffice. In this work, we study a notion called stone composition, which allows us to focus on the direct sum obstacle of this conjecture. And in particular, our result is a version of the weak conjecture for stone composition. Now, I'd like to finish with open problems which I think are nice and important. Just get rid of this annoying quantitative loss that we have in our result. I'll get to, and I'll say a few more things about it in a moment. Second, this result calls for depth complexity, but many other previous works in the literature about the KRW conjecture give lower bounds for a stronger complexity measure called formula complexity. And it would be very nice to see if we can get lower bounds, if we can adapt our results to get a lower bound for formula complexity as well. Now, let me mention that both two open problems might sound at first glance like kind of like technicalities, like technical exercises in optimizing parameters. But I really believe that they are not. And I really believe that in order to solve both of them, we will need to gain new insights that might be useful in attacking the original KRW conjecture. In particular, for the first open problem of getting rid of this loss, I actually have a counterexample that shows that getting rid of this loss would require substantial new ideas. Okay, this is all I had to say. Thank you very much.
Questions? So what depth lower bound do you get if you replace the 0.96 by 0.001?
Basically, the lower bound you get is, okay, if you replace this 0.96 by epsilon, you get a lower bound of 4 minus epsilon times log n.
So the best you get is 4 log n.
Yes.
Okay.
But if you, I mean, in order to get 4 log n, you would have to get rid of this loss completely. And this would, and if you did that, then you would actually get a separation of P from NP1.
Okay.
But as long as you're willing to tolerate such losses, you can get, in principle, arbitrarily close to 4. Again, it would require actually new ideas to get something better than 0.64, something like that.
Okay. More questions?